Green Pace Security Policy Presentation, Marcus Stanley, April 2025, and Project 2 Security Policy Presentation. Welcome everyone, I'm Marcus Stanley, and I'm excited to present the Green Pace Security Policy. This presentation outlines our standards, principles, and automated testing methods to ensure secure, consistent software development across our growing team. Slide number 2, Defense in-Depth Overview. At GreenPace, our security policy is rooted in the defense in-depth model. By applying layered security practices from code to deployment, we reduce risk across the entire application lifecycle. This policy standardizes our approach to secure development, including principles, coding standards, authentication protocols, and encryption. Geeks. Slide number 3, Threat Matrix. Here is the threat matrix. Each coding vulnerability is ranked by severity, likelihood, remediation costs, and overall risk. SQL injection receives the highest risk level due to its severity and exploitability. This matrix guides our focus on addressing the most dangerous threats first. Slide number 4, Justification Standards STD-001 and STD-002. We begin with two common vulnerabilities, data type STD-001 and data value STD-002. Issues both have moderate risk. These bugs often stem from user input or improper validation and are typically easy to fix with the right tools and careful type enforcement. Slide number 5, Justification Standards STD-003 and STD-004. String correctness STD-003 and SQL injection STD-004 carry significant risk. Buffer overflows from poor string handling can be exploited. SQL injection is extremely dangerous, especially when raw input is used in database queries. These are among our top priorities. Slide number 6, Justification Standards STD-005 and STD-006. Memory protection STD-005 is a major challenge in C++. Improper memory handling can lead to crashes or even code execution. Assertions STD-006 are less dangerous but useful during testing. They're rated low risk but are still valuable for catching logic errors. Slide number 7, Justification Standards STD-007 and STD-008. Exception handling STD-007 ensures stability during runtime failures. Without it, systems crash or expose data. Secure file handling STD-008 prevents information leaks and unauthorized file access. Both are vital for application resilience and integrity. Slide number 8, Justification Standards STD-009 and STD-010. Pointer safety STD-009 and concurrency safety STD-010 are high priority risks. Dangling or null pointers crash apps and introduce subtle bugs. Concurrency issues like race conditions are difficult to detect and must be prevented. Slide number 9, 10 security principles. These are our 10 core principles, from validating inputs and least privilege to using secure coding standards. Our 10 core principles guide secure development. Validate input data, heed compiler warnings, keep it simple, and apply least privilege are key. Every principle is linked to one or more coding standards that ensure these ideals are followed throughout our code base. They help align development with industry best practices. Each principle is backed by one or more coding standards to ensure proper implementation. Slide number 10, Coding Standards Overview. We've defined 10 coding standards, each mapped to a specific vulnerability class. They're prioritized by risk and complexity. SQL injection and memory safety standards are at the top. These standards form the foundation of our secure development lifecycle. For example, SQL injection, buffer overflow, and pointer errors are top-tier threats. Exception safety and assertion usage are lower risk but still important. This prioritization helps developers know where to start when securing new code. Slide number 11, Automation Table. This slide highlights how automation supports our security policy. From build to deployment, tools like CPP Check, Fortify, and Clang Tidy help detect flaws early. We've integrated these into our DevSecOps pipeline, ensuring every commit is scanned automatically. Slide number 12, Encryption Policies. We encrypt data at rest with full disk encryption, in transit using TLS 1.2+, and in use by limiting memory exposure and securely handling sensitive values. For example, our encryption policies are threefold. We encrypt sensitive data at rest using full disk and database level encryption. We use TLS to encrypt data in transit, and we mask or encrypt sensitive data in memory to reduce exposure while it's being used. This ensures that user data remains protected no matter how it's accessed or processed. Slide number 13, AAA policies. Authentication uses MFA to verify identity. Authorization is handled through role-based access controls. Accounting policies log all user activity. This AAA framework ensures transparency, security, and compliance across all systems. Slide number 14, unit test, buffer overflow. This test checks input length and boundary handling. Long inputs fail while safe strings pass. This confirms our input validation rules are effective and that string buffers are correctly handled. These tests prevent classic buffer overflows. Slide number 15, unit test, SQL injection. Here we test database query safety. Unsafe raw inputs fail while parameterized queries pass. These tests ensure all input is sanitized before reaching the database, protecting against injection attacks and unauthorized access. And slide number 16, unit test, memory leaks. This test catches memory management flaws. Smart pointers like unique PTR pass, while raw new allocations without delete fail. This highlights how our standards favor modern C++ practices for safety and stability. Slide number 17, unit test, concurrency safety. Race conditions are hard to spot. We simulate unsafe shared variable access, which fails, and atomic operations, which pass. These unit tests, paired with tools like Thread Sanitizer, help us write reliable thread-safe code. Slide number 18, automation summary tools. This automation summary reinforces our DevSecOps approach. Static and dynamic analysis tools are integrated at each CI/CD phase. They provide quick feedback, reduce manual review time, and enforce coding standards consistently. Slide number 19, risks and benefits. Acting now improves security and compliance. Waiting builds technical debt and increases vulnerability exposure. Fixing high-risk flaws like SQL injection and memory misuse has the biggest impact on system reliability and user safety. Slide number 20, recommendations. Current gaps include missing fuzz testing and centralized log visibility. We plan to introduce dynamic analysis tools and integrate dashboards for better oversight. This proactive step supports ongoing improvement and risk mitigation. Slide number 21, conclusions. Secure coding is not optional, it's foundational. To stay protected, we'll adopt secure libraries, enhance developer training, and use CI tools with security gates. These standards ensure green pace stays secure as we scale. Slide number 22, external testing demo. This demo shows real-world use of tools like CPP Check, Valgrind, and Fortify. These tools catch issues such as buffer overflows, memory leaks, and race conditions. Their output confirms our tests are effective and that we can catch vulnerabilities before they reach production. Slide number 23, references. Our policy is informed by trusted sources, the SEI CERT C++ guidelines, Microsoft's unit testing docs, OWASP Top 10, and industry tools like CPP Check, Valgrind, Fortify, and Thread Sanitizer. These resources support our technical decisions and security posture. Thank you for viewing the GreenPace Security Policy presentation. Our secure coding principles protect our applications and clients. Let's commit to security-first development and continue improving our tools, training, and testing.